Hi, this is Engineering Mechanics 1 Statics, so ME4111, and we're on to tutorial sheet 5, which is looking at equilibrium. So we'll just do a very quick run through of question 1, which is looking at free body diagrams. And free body diagrams are, I've said this several times, they're really critical to the whole solution process because they are your model of what's going on. So very often you're given a picture like this, or you'll be working off an engineering drawing or something, and you need to come up with your mechanical model of it that you're going to base your analysis on. And these questions here gave you some incomplete FBDs, so you're asked to complete them. So in this one, the two forces here at the reaction were missing, so AX and AY. So we had the force from the cable, we had the load from the crate, and we're missing the reaction forces here at point A. Now in this FBD, you can see that, okay, they're not drawing the cable. The system is this thing here. That's drawn in isolation. There's nothing connected onto it. Where we have contact with the cable is not drawing, we have the force. The crate is not drawn, we have the force arising from that. And that's one of the key things with FBDs is that instead of contact, you replace contact with forces. And when we get to the pin joint here, so we're told it's a pin support, no forces were drawn on the free diagram there, so that contact was not replaced with forces. Now, how did I decide that it's AX and AY that are pointing those directions? And why is there no moment reaction there? Well, one of the things you can do is you can look up for a pin joint what the support reactions are. Okay, so again, there's a table of stuff in the textbook that you can look up. The easier way to do it is just to use your common sense and to ask yourself a series of questions. If I push this in a particular direction, will this connection allow that motion or will it react to it? Will it try and stop it? So if I look at just this pin joint, so what I do is I cut it here and I cut it there and I forget about the cable up there, I forget the mass here. And what I do is I take this object, and if it is just here at point A, and there's no forces up there, no forces there, and I try and push it in the X direction in, it's going to push back, it's going to try and stop that. And if I try and pull it up in the Y direction or push it down in the Y direction, it's going to react. So I can have reaction forces that are in either of these directions. Okay, and I'll come back to how I decide the direction in a while. The other thing is if I try and rotate it. So if I try and cause a rotation, any direction, clockwise or anti-clockwise, just with that section, forgetting those loads, this pin joint will allow that rotation, so it is not going to react to it. And what that means is therefore that I have no moment reaction there. But if I do push it in the X direction or pull it or push it in the Y direction, I would expect a reaction. Now, the direction I've given to AY is positive. And that's because this force has one coming down and this one has one component coming down. So therefore, I expect that just from my experience that this will be acting up. If you're not sure, you just assign a direction to it. And your analysis will tell you whether or not your direction is wrong. Similarly with the X direction, this has a component coming that way. So I'm saying, okay, well, chances are this is going to go that way because this one is just constrained to the Y direction. So again, that's using my intuition. If I didn't know, I could assign it just any arbitrary direction. And again, my analysis will tell me whether I'm correct on that. So if I get a minus in my answer for a magnitude of force, that is telling me that in my free body diagram, that force is pointing the opposite direction to the way I have drawn it in the free body diagram. So again, the point here is that when you're solving equilibrium problems, you draw your free body diagram and your solution is based on the free body diagram. If you haven't drawn the free body diagram, you can't get a solution. So bear that in mind, and that's how I view things in the exam. I don't see how you can produce a solution to something if you haven't produced a model. And the free body diagram is your model of it. So it is very important that you do it. For second part of this question, we have this lever, which is applying a torque to the shaft at point O, so this point here. And we're given the force P pulling up. So we're given P, we're given the reaction force at this location here. And what was missing was the moment force, the moment reaction. So again, it is applying torque. So we have a couple will be set up by these. So there is a moment about this. which would be rotating in this direction. So I've put in the moment reaction going in the opposite direction to that. Okay. The next one here, we have this boom. Again, you can see that we've drawn the boom. That's in the free body diagram. We've replaced M with mg, so again, a force. The cable here, connection at B, is replaced with a tension. We don't care about any of this stuff, it's not relevant. We focus now on point O, and in the question we're given, there were no forces acting at point O. So again, this is a hinged joint. So if I try, again, if I just cut it here and I try and rotate this, that joint would allow that rotation, or it would allow it to rotate that way. So I'm not going to have any moment reaction due to that. But if I try and push it in the X direction, or pull it or push it in the Y direction, so either way like that or like that, I would expect a reaction. So I've assigned directions in the positive Y direction and the positive X direction to those. The positive Y, because this is a component coming down and this is a component coming down. So I have two coming down, so one of them must be going up. So they sum to 0. And again, this is a component coming across like that, cable T. So my guess is that the reaction at O will be acting in the positive X direction. Again, sometimes I can infer what direction they should be going in. Other times you may not be able to do so, so you just arbitrarily assign a direction, what you think best. And again, if you get a negative in your answer, it's telling you that your free body diagram is showing the force pointing in the wrong direction. Okay, the next one then is a crate, smooth vertical wall. So again, just a reaction force there, that's fine. Rough horizontal surface. Okay, so we were just given the reaction force. It's rough, so it can support a friction force. So we will have a lateral force there. Okay, and we have the weight acting down, which is fine. So this is the additional force that is required to complete the FBD. Okay, and I think this is the last one, is it? It is. Let's go back. So we've got this bracket supported by a pin connection at A and fixed pin in a smooth slot at B. So there's no friction in this. So we just have the normal contact, so that's fine. And we have the connection at point A. So again, it's pinned, so it will allow rotation, so we have no moment reactions. And we have a vertical and a horizontal reaction component to that. Okay. So again, just practice free body diagrams. Make sure that you're comfortable with them. You should always indicate in them your coordinate system also, so that it's obvious what coordinate system you're using. And just bear in mind that the whole idea of the FBD is that you're basing your solution off it. It's your model of it. So it's your presentation of how you're going to solve the problem. And if that is not presented, you cannot solve the problem. Okay, so you cannot get marks for a solution. So always make sure that you draw a free body diagram in equilibrium problems. Okay, so that's question 1. We'll move on to question 2 next. Thank you for your time. Bye-bye.